Okay, I've sent a request to share screen. If you can approve that.
Apologies.
Alrighty. You're keeping us waiting.
Okay, you should be able to share now.
All right, awesome. Thank you. Let's see. Alrighty. All right,
Hope you
sharing.
connected to the
I did.
right internet. Okay, great.
I learned from my mistakes, the errors of my ways. Alrighty. All right, can you see my screen? Should be able to see that now.
Yes, we are.
All right, let's let me expand it to full screen.
Yeah.
You can see full screen, right?
Yes, sir.
All right, awesome. All right, welcome everybody to our day 2. So today we'll talk about regression analysis. Again, we're not assuming knowledge, so it's going to be building from the ground up. So it's going to be very simple, and then we'll progressively build on that. All right, so I'm sure you guys have seen this picture before, the picture of a blind man on an elephant. And so the story goes that a bunch of blind men were put, well, not blind men per se, they were blindfolded, and then they were put in contact with an elephant, and they were asked to describe what they felt. And the guy who held the tusk said, "Oh, it's a spear." And the guy who held the trunk said, "Oh, it's a snake." The guy who held the leg said, "It's a tree." The one who held the tail said, "It's a rope." The one who felt the flank of the elephant said, "It's a wall." And the one who grabbed the ear said, "Oh, it's a fan. This is surely a fan." So the question is, who is correct and who is wrong? Well, the answer is that all of them are correct. But also, the answer also is that all of them are wrong. So the question is, how can they be both correct and wrong at the same time? Well, they're correct in that they were accurately describing what they felt. I mean, there was no error in that. They were wrong, however, because they failed to see the big picture. And that essentially is what happens when we look at individual data points. If you have, for example, a data set, rows and columns, remember? You can look at the particular row and say, "Oh, Alice, maybe this individual is Alice, right? Alice eats peanuts, and so she has allergies." And so you can say, "Oh, wow, eating peanuts gives you allergies." But that's just one data point. It doesn't tell any story, right? The only way in this case for this blind man or blindfolded man to see the big picture is to step away from the elephant. The problem is that they're too close to the data points. So when you're too close to the data point, you can't see the whole picture, right? You can only see the part of the picture that is in contact with you. And that's the problem. That's why we do analysis, right? The whole point of regression is that how do we get a bigger picture of this elephant? And the only way to do that is for us to step back, right? To regress. And that's what regression is all about. I love etymology, which is, the study of origin of words. It helps us to develop insights into what things mean. So etymology means to step, regression or regress means to step back. I'm sure you've heard somebody say in school that, "Oh, are you regressing or what?" When their little cousin is not doing well in school. So you ask that, are you regressing? Because it's like you are stepping back from where you were before. So regression is all about, let's take a step back. Let's go backwards. And why are we going backwards? Well, simple, so that we can see the big elephant, because we have realized that when we're too close to the elephant, we see just that data point we're in contact with, but not the whole big picture. And therefore, there's a need for us to step backwards so that we see the whole big picture. And I'm also sure you've heard this saying that, "Oh, he or she can't see the forest for the trees." What that simply means is that the individual, in this case, literally is standing too close to the tree. So if you're standing next to the tree, obviously all you can see is the tree. However, if you want to see the whole forest, you have to move backwards. You have to go a lot higher, right? Away from that individual tree. That is what allows you to see the entire forest, not just an individual tree. As you can imagine, the higher you go or the backwards you go, you lose sight of the individual details of this particular tree. You can't say that, oh, wow, this tree has some greenish stuff on its bark. You lose that detail, but what in exchange of what you have lost, you gain perspective, you gain the big picture of what the whole data is telling you. The same thing applies to like space. None of us has ever seen the Earth like this while walking on the Earth. We're all on the Earth right now, but we can't see this picture. Why? Well, because we're too close to Earth. The only people who have seen a picture like this with their eyes, naked eyes, are people who go to outer space, because now they've regressed away from the Earth, and so they can see the big picture of the Earth in its entirety. And so, again, so that's just a way of reinforcing the notion that we got to step backwards. Now, when we're stepping backwards, there are two ways we can step backwards. So here is the first guy. Let's look at two things we're focusing on. The thing we are trying to study, which is like the elephants, right? We're stepping backwards to see the whole elephant. And then we have the thing that is doing the studying, right? We want to study the elephant, and we have the predictor which wants to study the whole elephant. So there are two ways we can look at this. We can say, oh, let me just point my telescope to see what I can find. In this case, we don't have a very specific thing in mind we want to find. We're just saying that I'm just going to cast my telescope up to the skies and just let me see what I can find. We call that kind of analysis exploratory. You don't have a well-defined hypothesis in mind. You just want to explore. So you see things like factors associated with XYZ. Well, that kind of research question means that you don't have a very specific hypothesis in mind. You're just exploring to see what might be associated with this outcome. That's exploratory analysis. Or the alternative is to say, let me point my telescope and at a very specific star to see how bright it is, to test my hypothesis about its brightness. In this case, that's confirmatory, right? You have a very well-defined hypothesis in mind, which you wish to explore and test. So the same thing applies with regression. When we're doing regression, it could either be exploratory, where we're just trying to say, oh, what are some of the factors that might be associated with this thing? Or it could just very well define and more causal models. So here is a pop quiz for you now. Just test that you have been paying attention. So for each of these questions, I want you to tell me whether it is exploratory or confirmatory, right? So you can use E or C. So just put your answer in the chat. So what we're asking is there a well-defined hypothesis here, which is C, or is this just a fishing expedition? Well, not fishing expedition is too negative. It's just exploratory. All right, the first one is, what factors most influence customer satisfaction in online retail environments? Is that E or is that C? Again,
E.
Okay,
A lot of
good.
E.
All right, that's excellent. So you guys have definitely been paying attention. Question number 2, does increasing dosage of drug A reduce anxiety symptoms more effectively than the standard dose?
C. C.
Okay, is there any E there?
E. C.
Very worried.
Yes, E.
Okay. All right. But I hope there's more of C's than E. It's definitely a C. There is a very specific thing you are looking at.
Yep.
If it's E, you will have been saying, oh, what factors are associated with reduction in anxiety symptoms? But that's not what we're asking. We're saying, does this very specific thing result in this very specific outcome? So that's confirmatory. All right. Question 3, how do social media usage patterns vary across different age groups? E or C?
E. E. E.
Excellent.
Lots of E's.
All right, excellent. What are the emerging trends in remote work preferences post-pandemic?
E. C. E. C. E.
Okay,
E.
it's definitely an exploratory, because we're just trying to see, oh, what is happening in this, what's happening these days? We don't really know. We're just trying to see what's happening exactly. So that makes it exploratory. And then lastly, does a high protein diet lead to greater weight loss compared to a low protein diet over 6 months? E or C?
C. C, C, C,
All right, good.
and C.
You guys definitely were paying attention. So, all right. Now we can't talk about regression without talking about models. We'll talk about regression modeling. So that means that we need to know what models are in the most simplest sense of the word. So when we say model, what does that mean? Now, who can tell me what this picture is? What do you see on the screen? You can type or you can answer. You can raise up your hand, whichever is appropriate. So what do you see on the screen?
Red apple, 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 red apple.
That's all wrong. Now, I need you guys to be very, very specific, right? We're now in
Representation of an apple.
wrong. Well, kind of. Now, I need it to be a bit more statistical now. Precise and with some more statistical flavors in it. All right, so what is this on the screen?
Model of an apple. Model of a
Excellent.
red apple.
Okay, good.
Representation of
All right, you get the
sample
point.
of a larger population. Okay.
Okay, all right, you get the point. This is a model. This is not a. So why were the previous answers wrong? Why did we reject all the other answers that said this is an apple or this is a red apple? Why were those answers rejected? Why did we soundly reject those answers? Any thoughts? Why do we say
Because
this
it's
is
not
not
a
an
real
apple?
apple.
Excellent. Now, what can you do with a real apple that you cannot do with this apple?
Someone mentioned that this one cannot be eaten.
Excellent. So if we cannot eat it, we cannot taste it, why is it useless then? Why then do you need it? Like, why do you take the effort and time to paint it or take a picture of it? Like, why do we set about creating in the first place if we can't eat it or can't taste it?
To represent the real one.
Okay. And why might we need to represent the real one? In what context, for example? Well, we need to answer these questions to understand why we model.
To describe.
Yeah, describe to who?
To teach.
Okay.
As a representative of the real, when we don't have the real one, visual
Excellent.
understanding.
Okay. All right. That's the punchline we're looking for. Can you emphasize that punchline once more so that all of us, including those at the back, we hear clearly?
Visual understanding.
The other, yes, the next phrase. In what
To
situation?
conceptualize. Okay. I read a lot. Perception and
When
ability to think about it.
when we don't have one.
Representative of the real. Okay. When you don't have the real one.
Exactly. When we don't have the real one. If I have a real apple, it does not make any sense giving a picture of an apple and say, hey, this is an apple. Oh, I'll rather give you the real apple, say, hey, dude, this is what an apple looks like. But there may be contexts where I may not have a real apple, right? For example, in some parts of the world, there are no apples. So it's possible that the individual has never seen an apple, right? The child may have, yeah, I mean, I can think of many circumstances where somebody has never seen an apple before. But when they're teaching them A for apple, I mean, you have to show them something, right? And that's where the model of an apple becomes important because we do not have the real apple. So that sets the framework for you to understand why we need models. We need models because we don't have the what? Fill in the blank. Models are required because we don't have the blank.
Data.
Excellent. Right? So since we don't have the full data, we say, well, half bread is better than none. So how about we create a picture of what we think reality is like? And we understand, obviously, that with this picture we're creating, we can't eat this, we can't taste it, but it looks close enough to explain to somebody who has never seen an apple what an apple looks like, right? So that's exactly why we create models, so that we simplify reality in the event where we don't have data, so that people who don't understand that reality can at least see the simplified version of truth and say, oh, I see. oh, I see, this is how an apple looks like. So maybe when I look at the real apple, I will be able to link them and say, oh, this definitely match up. And that's why we need models. So models give us a simplified version of reality so that we can communicate in the absence of full data. That's why we need models. I'm sure you've all heard the saying that all models are wrong, but some are useful. Of course, there's no picture of an apple that you can eat and taste. In that context, all models are wrong, but they're still useful to explain the reality to some individuals who may not have the data in a way that they can understand. Now, when we're fitting models, again, we come back to this picture. We will always refer to this picture. Three phenomena that explain anything are truth, chance, and bias, right? This should be fused into your brain because, this is the bedrock of epidemiology and research. It doesn't matter what your field, whether you're in sociology or medicine, right? The pursuit of research is the pursuit of truth. And the pursuit of truth means that we have to look for things that undermine the truth and get rid of them, right? Like bias and chance. So that when we look at the truth, we say, this is the truth, right? We do this in all aspects of research, including when we're doing regression modeling. So pay attention to some things we'll be talking about, and those link directly to this picture of saying we want the truth, but we want to isolate the truth from chance and from bias, because that's what we want. Now, what kind of truth? Well, they say there are many shades of truth. You can have the whole truth, which is on the left-hand side, or the whole truth, the one with holes, right? Obviously, we don't want the one on the right. We want the whole truth and nothing but the truth. And so that means that when we design studies, when we're modeling, we need to go back to this picture. Always freeze this picture in your mind, right? Truth, chance, and bias. This is a summary of research. If we were to ask to summarize research in one picture, this is that picture, right? The pursuit of truth, but we have to somehow control for bias and control for chance. And that's what we do research. If we don't control for those, what we have is just the whole truth, which is the truth with holes, right? Because what you're giving us is maybe some version of a truth, but it's contaminated with bias and with chance. So that's what we're trying to eliminate. And so when we do regression modeling, you will hear things like adjusting for so and so, or controlling for so and so, right? What do those terms mean? Well, this is a very simplified picture of what this means. If you are in an airplane when, maybe they are serving food or whatever, they tell everybody to please sit down and strap in their seats, right? They are controlling for motion that you might cause, right? We just want to focus on only one person at a time, the person who is serving the food, right? That reduces accidents, there's less confusion, everything is clear. It is the exact same thing in your regression model, right? I'm sure you've heard the saying that we can all sing together, but we can't all speak together. That means that we have to take turns speaking. You see how we're speaking now? I am talking and you are quiet. If you want to talk, I have to be quiet. We can only speak one person at a time. In your regression models too, that's the exact same thing that must happen. If one variable is speaking, the others must be quiet, right? And that is what we mean by controlling for X, Y, and Z. We mean we want to keep them in their seats, strap them on, and make sure they're quiet so that the only person whose voice we can hear is the variable that is speaking, right? So we're going to look at this when we go on to the hands-on part of our lecture and see how those things work out. But the goal now is for you to have a big picture understanding of what those things mean, very, very high level. So you can see, oh, wow, okay, this is why we're putting those variables. Why are we putting those variables in the model? Well, we're putting those variables in the model because we want the whole truth. Why do we want the whole truth? Well, we want the whole truth because the truth could be contaminated by bias and by chance. And so regression is a way to eliminate the role of we can have just the truth. The whole truth, I mean, the one on the left-hand side. And so to do that, we have to control for the influence of those other variables that might be introducing bias. So you can see how everything fits in together. All right. We cannot talk about bias without talking about internal and external validity. Those are things that we need to be aware of. Internal validity means truth within the study, right? So it means to what extent is your study free from those biases we mentioned? Selection bias, confounding bias, measurement bias. Those are the three biases we talk about in epidemiology, right? So when we say internal bias, there's internal validity, which means that you have protected your study from those sources. So let's go back to this. We mean that you have the whole truth. And why do you have the whole truth? Well, because you have taken care of chance and bias. This is what we mean by internal validity. The extent to which you have only this one remaining and you have eliminated these two guys, right? If you have done that effectively, we say, yes, your study has internal validity. External validity, however, refers to generalizability of the study to other populations, right? You can't talk about external validity if you have not resolved internal validity, because, like, first and foremost, you have to take care of yourself, and then you can help others. Like, you can't give what you can't have, what you don't have, right? If you don't have validity in yourself, how then can you give it to other people, right? In the same vein, the study has to have internal validity in of itself first, before we can talk about external validity, which means how do we then generalize the truth from that study to other populations? If it doesn't have truth in itself, then that's a moot point. It's dead on arrival. All right, so we need to understand what these biases are. So if we think of a study as being just a combination of people. Oh, say, oh, I'm doing a study. It's always I have people, but it's not just the people we're interested in, right? It's their answers, right? So we have people, but we're ultimately interested in their answers. So if we consider that a study is made up of this, then we can then understand how those three biases fall into place. Again, remember, the take-home message for today is research is all about truth, chance, and bias. And bias means selection bias, measurement bias, and confounding bias. We need to eliminate those things. Selection bias has to do with how people come into the study and how they leave, right? So if there's a systematic difference between those who leave and those who stay, or if there's a systematic difference between those who enter and those who do not enter, then you have a problem on your hands, right? So there are two arrows you want to pay attention here. How do people enter? How do they leave? If there's something sketchy about how they entered or something sketchy about how they left, well, you have selection bias, because this means that if there's a sketchy mechanism here, it means that these guys who are entering are different from those guys who are not entering. If there's a sketchy mechanism here, it means that those who are leaving are different from those who are staying. Either way, the study has selection bias issues. So that's what selection bias means in a nutshell. All right, we're not going to go into the weeds. But the goal is just for you to have a big picture understanding of what those things mean at a very simplified level. Confounding is a noisy neighbor, it's a nuisance variable, right? That's what we call it also in epidemiology, a nuisance variable. It's like you're trying to have a conversation with your guest, and this noisy nuisance guy just keeps interrupting the conversation. And so that means you can't really hear the conversation between those two characters very well. So confounders introduce noise so that we can't hear the conversation occurring between the exposure and the outcome, right? So obviously we have to take care of them to hear everything clearly. Again, all of this boils down to why we do regression. See, we're not just jumping into fitting regression models and explaining them, because we need to first of all understand why we fit regression. So, right, what are we trying to achieve? We're trying to achieve a state where we extract the truth from bias, right? We want to control for bias, the biasing influence of variables like nuisance variables or confounders. So that's the big picture of what we're saying. And then measurement bias means that we didn't measure things well. There's noise in how we measure things. Keeping it simple. All right. So let's connect what we're learning today with what we learned yesterday. So yesterday we talked about univariate analysis and bivariate analysis. So regression, multivariable regression is this last element here, right? And this is how we structure our analysis. We first of all handle univariate analysis, then we'll move to bivariate analysis, and then we'll move to multivariable analysis. Again, we talked about this yesterday. But for those who weren't here, univariate analysis is saying, oh, what's the mean value of X and what's the median value of X? We're interested in just one variable at a time. Uni means one, like the word unity means one at one. Again, we're here again, bivariate means bi means two. So here we're interested in two variables. For example, we're interested in, does the mean value of X differ between boys and girls? Is mean height different between boys and girls, for example, right? There are two variables here that we're interested in. One is height, the other is gender. That makes it bi or bivariate. Then multivariable analysis is now when we have multiple variables. We're trying to say, oh, we're interested in the mean height of comparing the mean heights between boys and girls, but we suspect that other things apart from their gender or sex may be at play. Maybe girls have come from richer families, or maybe there are some other factors at play. And we want to control for the noise from those other factors. That's why we do regression, right? So it's your job as a researcher to know when you need to do regression, when it's needed, and when it's not, right? If your study is just a plain descriptive analysis, well, you don't need regression then. If I'm just trying to look at, oh, percentage of people who smoke cigarettes, that's the goal of my analysis. I just want to see in the world population, what percentage smoke cigarettes and how does that differ by gender and race? Well, that's fine on of itself. So the take-home message is not that every paper you do must have a regression in it. No, that's not what we're saying. What we're saying is that you need to know when you need to do a regression. And that is particularly important when you have a causal question in mind. Causal question like, what is the effect of A on B? Or what's the association between A and B? So the issue here is that A and B may have an association, but is it the truth? Are there other confounders at play, right? So we don't always need regression, but you need to know when regression is needed and execute accordingly. All right, so let's go ahead and look at some types of regression and how we can fit the regressions and how we can interpret them. For the sake of those who prefer using other programs like R, I'm going to use examples in the public domain so that you can refer to them, since this class it's not about programming. We're going to use the Chi-Squares platform for all of the work we're doing. But this way, if you're interested in, going to see how the code is structured, this gives you an opportunity to also, have access to such code. So for that reason, I chose to use work in the public domain so that we can, whether you're using the Chi-Squares platform or you want to go and write your own code, you'll still be able to find it relevant. But here, let's give a very broad overview of what we're going to be doing and what kinds of regressions are needed for what scenario. So here, first of all, when we have a binary outcome, binary means two. So there are two outcomes, two categories to that variable: dead or alive, sick or well, 0 or 1. That's binary, right? So when you have a binary variable, the analysis that you could do could be a binary logistic regression, which calculates odds ratios, or you could use a probability regression. You could also use a Poisson regression to calculate, prevalence ratios. One of the misconceptions people usually have is that, oh, is a binary variable also a count? So when you talk about using Poisson regression for binary variables, many people get confused. They're like, oh, but we thought that Poisson is only for counts. Well, a binary variable is a count. If you have 0 and 1, that's still a count. It's just that the count is truncated at 1. So in general, we prefer prevalence ratios when the outcome is very common, because odds ratios tend to exaggerate the effect size. And so for that reason, prevalence ratios are preferred by most journals when you have a very common outcome. But in general, what we're seeing is that when you have a binary outcome, you could use a binary logistic regression, you could use probability regression, you can calculate prevalence ratios also in the Poisson model. Yeah, you don't have to memorize all of this. We're going to look at it. So this is just to give you a very high level. So don't worry about memorizing anything. When you have a categorical variable with 3 or more levels, what you need to ask is, these categories, are they ordinal? Remember, we talked about ordinal and nominal variables yesterday. Ordinal, the word order, from the word order, means that there are orders. There's an inherent ordering. If there's inherent ordering, you will use, as the name implies, ordered logistic regression. If there is no ordering or it's nominal, you're going to use nominal regression. Multinomial means from the word nominal. So nominal for nominal, ordinal for ordinal. So it's pretty simple, right? If you have many categories and they're ordinal and they're ordered, you use ordered regression. If you have many categories and they're nominal, you use nominal regression, also called multinomial regression. If it's a count variable, counts means things that we can count, right? Number of cars and all of that. Then the question you have to ask is, this variable, is it equidispersed? So in other words, you are looking at whether the mean is roughly equal to the standard deviation. You don't have to look at it from a very theoretical framework. Just think about how the event occurs. Let's say, for example, you are a farmer and you are looking at number of deaths of your livestock across the 12 months of a year. So the question you're asking is, are the number of deaths roughly equal across the whole 12 months? So that maybe roughly every month I have 50 deaths. That means that there's not a whole lot of variation in the number of deaths. But in the real world, that doesn't really happen, because in some months of a year, you may have like a pestilence or some disease among the livestock. So you may have like 2 deaths in January, 10 in February, then like 400 in December, whatever, right? That is highly over dispersed data, because you can see huge amounts of variation in the data. So what we're saying here is that when you have a count variable and you have such phenomena where you have drastic variations in the outcome, that is why we have negative binomial regression, right? It's very appropriate for over dispersed outcomes. But if everything is very quiet and calm and it's about the same, then you use Poisson regression. Now, sometimes you have what we call excess zeros. Excess zeros means that there are 2 sources of zero. Think of it as a true zero and a fake zero. That's a very simplified way of putting it. But it means that zero could come from 2 sources. Zero could mean that so let's say, for example, I ask everybody here, how many cigarettes have you smoked today? Well, I'm sure a lot of people will answer 0, right? Now, if you analyze that 0, we have 2 sources of 0. The first source is people who actually smoke, but just haven't smoked today, right? So their 0 is like, okay, I am a smoker, I have not smoked today. That's where my 0 is. But then you have people who just don't smoke. And so their 0 means, I am not a smoker. I don't know what you're talking about, right? So you see here that there are 2 sources of 0 apart from, the research question you had in mind was, what factors are associated with the rate of smoking, right? Well, among smokers. But now you have zeros coming from smokers who just haven't smoked today, and then zeros coming from this other population who never smoke. So that 0 means I don't touch that thing you're talking about. So that's what we mean by excess zeros. The zeros are coming from this population that is not even part of your population of interest, right? So when you have that kind of scenario, you'd have to use a different model. So what happens what your software is doing is that it's actually fitting 2 separate regression models. One, a binary logistic regression model. The other is for a Poisson model to estimate the count, right? Well, not to bore you with the details, but that's a special model when we have an excess of zeros. So when you do that, and this is where context is needed. Context is king, because you are the only one who has that context to know that these zeros actually are coming from people who are non-smokers. There's no way a computer will just know that, right? You have to supply that context. So this is why we always emphasize the role of context in data analysis. Now, if you have a numeric variable, if it's, if it meets the assumptions of linear regression, then we use linear regression. Otherwise, we can transform, we don't just transform in all scenarios, right? For example, log transformation is very specific for scenarios where you have non-negative values, non-zeros, and you have, they're right skewed, right? Right skewed data. If your data is left skewed and you transform, or you have negative values and you're transforming, you're actually doing more harm than good, right? So in some instances, you should know that, no, this makes no sense. And that's one of the value propositions that the Chi-Squares platform does. It inspects the nature of a variable, and the options that it's giving you to do are all are all appropriate to the nature of the variable, right? So, but it's very important for us to also know the underlying assumptions of these things. Or you can use median regression, which is just estimating medians as opposed to means. And then if your outcome is a date variable, you can use, where you're looking at time intervals, you can look at time to event analysis, you can look at interrupted time series analysis. We won't go into all of those details, in a future session, we're going to just focus on how do we analyze time, right? And that workshop will focus on things like interrupted time series analysis, survival analysis of, temporal trends with equal or unequal time periods, and so on and so forth. But for this session, let's just keep things pretty simple. All right, now let's go over to our demo and look at how all of these things fit together in practice. So we're going to just pick each of these ones here and look at the implementation in whichever program it is, and then also replicate it on the Chi-Squares platform. I have downloaded the data sets they use, so we're going to share the data sets, and that will be your homework for today to replicate whatever it was that we found. So let's go ahead and get started. So for those of you who are joining us today, to access the Chi-Squares platform, you go to the website here and you log in if you have an account, or you sign up if you don't have an account. All right, let's go to analysis and let's create a new project. This was our project from yesterday, day one of the analysis workshop. We're going to start a new project now. We're going to call it, I'm looking away from the camera because I have two monitors, by the way. Day 2 of analysis workshop. Okay, so this covers analysis and interpretation of various regression models. All right, let's upload this. So the first one we're going to focus on is, let's just start with Poisson, since it's first on the list. So again, pop quiz. When do we use Poisson regression? I want to make sure you've been paying attention. What kind of outcome would we model with Poisson? You can type in the chat.
When it's continuous.
No.
Count.
Count. Exactly. Yes. All right. Awesome. Yeah. Count. When is count and what? Is it all count?
There's also binary count, and the SD equals to the mean.
Okay, good. All right, so I'm going to throw some scenarios and let's hear you provide the answer. You have count data and it's equidispersed. What will you use? Count with equidispersion. Equidispersion means roughly equal amounts of mean and standard deviation.
We have Poisson.
Poisson. Count with overdispersion.
Negative binomial.
Okay. Count with excess zeros.
Well, negative binomial,
No.
zero inflated.
Exactly. Zero inflated. All right, good. You guys have been paying attention. All right, now let's take this Poisson first. Now that we understand what Poisson is all about, let's put the link here. So this is the data. So yeah, for those of you, this is for those who want to suffer, right? See, this is a lot of, a lot of output to just generate this model and interpret it. So again, for those who would want to write code, this is here for you. We who don't like to suffer, we're just going to fit it in the Chi-Squares platform and see what it is and how we interpret it. All right, let's do that. So let me read in the data. I'm going to share the data sets with you. This came from the site. So Poisson. All right. So this is the data set we have here. As always, whenever you bring a data set, please do not just jump into your analysis, right? You should always inspect the data, see what it's like. First, I always use these icons. I'm a huge fan of these icons. That allows me to, I'm a very visual person, so it allows, I can see that, okay, this is count data, or numeric data, this is categorical, this is continuous. Against what I mean, if you're importing a data set, you already know what to expect, or you should know at least have some expectations about what the data would look like, the variables look like. So when you import, always inspect your data. That includes visualization to make sure that things are the way you expect them to be. So let's look at this. All right, now let's go to the model. Let's jump straight into the model and let's see how we can first fit the model and, more importantly, interpret it. So this data set, let's look at what it's all about. So in this example, number of awards is the outcome variable and indicates the number of awards earned by students at the high school in a year. Math is a continuous predictor variable and represents students' scores on their math final exam. And prog is a categorical predictor variable with 3 levels, indicating the type of program in which the students were enrolled. So, so you have, this is essentially the context we need to look at. All right, so let's look at the model here then. Let's fix the model. Let's focus on how do we interpret it. So our outcome here is number of awards. Again, that's a count variable. So we'll come to estimate. We'll come to regression models. We'll select Poisson. Now, if you don't know how to select, let's go back. Let's take a step back. This part of the Chi-Squares platform is reserved for people who don't know what they're doing, right? If you don't know what you're doing, or if you're lost, you should always come to Analysis Wizard and say, hey, I have no idea what I'm doing. In this case, for example, you will come to Regression Analysis Checker, and it will tell you, oh, yeah, this is your variable. Yeah, you definitely need to use a Poisson model, right? So this is for people who don't know what they're doing, now who need guidance. So you should always live inside this Analysis Wizard. If you know what you're doing, you don't need to say, or you don't need the computer to tell you what to do, right? So you can always come here and say, in this case, I know what I'm doing. Well, we're just replicating this example, so we don't have to go through that path. But in case you did not know that it was Poisson, you don't have to memorize that sheet, that sheet we talked about, right? The platform will automatically tell you what kind of variable what kind of analysis is appropriate. It will, all these assumptions that are required, it will test them by itself in the background and say, oh, okay, this variable it's equidispersed. Okay. So you don't have to worry about, oh, how do I test for equidispersion, or how do I test that this is overdispersed? All of that is done automatically in the background by the platform. All right, let's go back to our story. So Poisson regression here, the outcome is number of awards. As you can notice, the platform automatically filters out all variables that are not count. So that all we're left with are count data. So we're going to select number of awards. That's a count variable. Next, we have to select the predictors. Our predictors were program type and math. So let's go back here. So the program type and math. The order of the variables listed is a function of how you check them. So if I selected program first, then math, that's the order in which they will appear. If I selected math first and then program, that's the order in which they're going to appear. So once we're done selecting, we click done select. Oops. Let me move this out of the way. So done selecting. The platform automatically selects reference groups for you. All right. And the reference groups here are based on statistical considerations. And in this case, it will automatically select the group with the largest sample size for you, because to ensure sufficient power, right? So here we see that automatically the platform selected academic as our reference group, which is the one with, the sample size here is 105 people. But you might have other preferences. You might have other reasons why you might want to select a specific reference group. In this case, for example, we might want our reference group to align with what is in this particular stuff, right? This is not super clear, they're using numbers, but anyway, but the point is that you should be aware of your choice of reference groups because it will influence your results, right? Whether we choose this one or this one will change the result because we're saying this is the one we're comparing our results to. It's like the reference group is like the army who's leading the general who's leading your army into battle. Surely you can understand how the choice of general affects the outcome of a war, right? If you use a weak general, well, you're going to lose the war, most likely, right? If you use a strong general, well, you might likely win the war. The reference group also influences because the reference group is saying, yeah, this is the guy who's leading us into battle, right? That's a very rather cheesy illustration, but I hope you guys get the point. So here, let's choose general as the reference group, because I'm sure that's what is selected there, and let's estimate that. So we'll then compare with the result and then see how that compares. All right, so here we have the output here. Let's first of all make sure that's the same reference group they used. Let's go back to this. All right, 2.91. Let me see. 2.91 for 4. All right, yes. All right, so here, first of all, let's compare the results, first of all. Math is a continuous variable, and for continuous variable, we are modeling per unit increase, which means that the way you interpret the results is from one point to, as we move up and up with every unit increase. In other words, if math is measured in points, let's say points from 0 to 100, per unit increase means as we move from 0 to 1, or from 1 to 2, or 2 to 3, in other words, with each higher step, this is what we get. That's what per unit increase means. Unit means 1. So per unit increase means that we don't have a fixed reference group, but we're just saying that as you move from one level to the next point, like that's the context in which you interpret the results. So program here, that was the second predictor, had 2 categories. The reference group is generally not displayed. In this case, the reference group was general. So every result presented is presented in relation to general. So that's why you have 2 results for the variable program, even though program had 3 categories, right? Because the guy who is leading the charge is not counted. We are comparing results in the other groups to that group. So you have 2 results here: academic versus general, vocation versus general. General is a reference group, remember? So here you have the incidence rate ratios. So that is what we calculate when we fit a Poisson regression model. We get incidence rate ratios and 95% confidence intervals. And here are the p-values from that, right? This is the this is the unformatted results with the intercept. The intercept is the result when all predictors are at 0 or at their baseline. So here we're saying that what is the outcome, what's the number of awards when you have math at 0 for those who scored 0 in math, as well as for those who had the reference level for the program. So in other words, the intercept tells you the expected level of the outcome when everything is at 0. Whatever 0 means the lowest level. For the math score, we're talking about you had a literal score of 0. And for program, we're saying for those who were general, right? This gives you the incidence rate ratios. And so the interpretation of this, so let's first of all compare back with the results here and see any differences that we might see. So number of awards for math, we see 1.0726. So here we're rounding to 2 decimal places. That's why you have 1.07. But if you want the full expression, 1.026, whatever, it goes on. But the formatted results are here to present the result in a way that is suitable for publication. And in general, present results in regression to 2 decimal places. So that's why the formatted result is presented to 2 decimal places. That's why you have it like this. And then the next one is the program, 2.95600, whatever. Let's look at the results here. 2.96, of course, it's rounded. If you look at the unrounded one, it's exact same value, right? Of course, you're going to get the exact same value. It doesn't matter what, it's like doing 1 + 1. Every calculator should be able to give you 1 + 1 is 2. So, but this is just compared to let you, for those of you who are going to use code to know, or who are using the software, regardless of what you use, you would know, you should have assurance that you are going to get the exact same answer, regardless of procedure, because this is just statistics. Statistics is based on rules, and rules are always dependable. All right. Now, how do you interpret the results? Well, this is what you're provided in. So first of all, let's look at the plot. The Chisquares platform always provides plots for every single operation that you run because, well, they say a picture is worth 1,000 words. So by looking at the picture, you can be able to better visualize things. Like this one, for example, if I look at the null value here, the null value here is 1. In all ratios, the null value is 1. And that should make sense because a ratio is a number at the top divided by a number at the bottom. So if the number at the top and the number at the bottom are equal, well, that means that their quotient results into 1. So a null value means, yes, in any ratio, odds ratios, incidence rate ratios, or relative risk ratios is always 1. So the value of an image like this, or figure like this, that allows me to immediately see which results are significant, right? And so here you can see that the rule here is simple. If the confidence interval crosses the null line, that means that result is not significant because it has 1 leg here and 1 leg there. So that means that it's not significant, right? If it doesn't touch the null value at all, that means it's significant. So when we look at the confidence interval here, you can see how that it's quite clear of the null value. So the image here is to allow you to be able to visualize the data in a way that is very intuitive. And again, like we said, the picture speaks 1,000 words. So every single operation you run on the Chisquares platform automatically generates an image or a figure to visualize the story so that you focus more on understanding what the results are instead of just generating numbers which you may not understand the context. The platform also writes out the results for you. It writes out the methods, it writes out the results, and the limitations. So, and the way it writes the results is that for results that may be more technical, it first provides you with some interpretation of the result, a framework to understand the results. So for example, this part here tells us that the presented effect measures are incidence rate ratios, depicting the impact of a 1-unit change in the independent variable or the predictor on the incidence rate of the outcome variable, keeping all other confounders fixed. as an example, an incidence rate ratio of 0.22 for a continuous predictor implies that the incidence rate of the endpoint decreases by 78% for every unit increase in the predictor variable. Whereas an incidence rate ratio of 1.64 implies that the incidence rate increases by 64% for every unit increase. So when the value is less than 1, all you're doing is that you take that number and subtract it from 1. So 1 minus 0.22 will give you 0.78% and multiply by 100. So if you subtract this number from 1 and multiply by 100, that gives you 78%. If you take this number here and subtract 1 from it and multiply by 100, that gives you 64%. So for every result that is a bit technical, the platform will automatically, first of all, generate a context for you to understand the result. And of course, the examples and everything here are completely stochastic. So that means that this text is completely different every run of the analysis you do, right? It's so it's not as if everybody now has that text. And then it now goes ahead to give you the results interpretation for this particular analysis, right? The first one was just a framework for you to understand the results. Now, this is the actual interpretation of those results. So this one says that, this is just referring to the results here. The following factors were positively associated with number of awards at the designated threshold level. Program coded as academic versus general with incidence rate ratio of 2.96 and the confidence intervals 1.55 to 6.4. And math coded per unit increase with incidence rate ratio of 1.07, right? Then all the other results were not statistically significant. Then because we have results here that, like this was not significant, right? So this takes the burden off you, right? If you can't count the number of papers where people literally butcher the interpretation of results. So the whole idea of this is that, well, you can be sure that this is perfectly interpreted, right? Now, your job is now to understand it, right? And then to make sense of it. And then if you're writing a manuscript, you can then choose to push the results to your manuscript. So if we're, for example, to push this to our manuscript, all we need to do at this point is to come here and just push the results. We can create a new manuscript and say Poisson regression analysis of factors associated with number of awards. What factors are associated with? I'm just putting in some fluff here, but with number of awards received. To explore what factors. All right, so now we can start our writing and then push the results to this manuscript. And so the platform will then push the results accordingly to our document, and then we can write out our context and continue with our work, right? So this way, again, the focus is then on how do we make sense of the findings we have seen, because now everything that we need is in the table. We have table 1, which came from our analysis, and we have a denominator, a footnote. Each table comes with a footnote in the main text. So this is telling you that the denominator for your analysis was all individuals, and that we're unweighted because we didn't weight these data sets. The same thing here for the figure. All right. Now let's go back to switch to analysis. Day 2. Alrighty. All right, so that covers that for Poisson regression. Now let's move on to the second regression model we had on our list, which was binary logistic regression. Let's look at that. All right, so here it says this page shows an example of logistic regression. Most times when people say logistic regression, they mean binary logistic regression. We should just develop the habit of being very precise in our language, because binary logistic regression is not the only type of logistic regression that exists. You have ordered logistic regression, you have multinomial logistic regression, and so on and so forth. So let's develop that habit of being very precise. So binary logistic regression, that's what we're referring to here. All right, so this page shows an example of binary logistic regression. The data were collected on 200 high school students and has scores on various tests, including science, math, reading, and social studies. The variable female is a dichotomous variable coded 1 if the student was female and 0 if male. Because we don't have a suitable dichotomous variable to use as our dependent variable, we will create one based on the variable right. And so this is how they create this. They said they use a cutoff of 60 or more. All right, so let's import this data set and let's do exactly what they did. And let's compare our results with what they have here and see how we interpret those results. All right, so I'm going over to the Chi-Squares platform. We're going to replace our data set now with binary logistic regression. Again, we're going to share the data sets with you after the class so you can practice as well. Those data sets came directly from those websites in the public domain. All right, so this is the data set we have. It has 200 rows. It's unweighted. So the first step here is to do what they did, which is to achieve this step. They took the variable called uncomp and so honors composition and divided into two groups at this cutoff value. So they took the variable right rather and divided into two groups and then created that variable uncomp, right? So let's do that. So let's look for the variable right and let's split it into two categories too, because binary means two. So let's go to Chi-Squares platform and do exactly this. So we're looking for the variable. We want to do a recode with the visual method based on the variable right. So select that. All right, that loads the variable. And they split the variable at the cutoff of 60. So let's split our variable at 60. So just click anywhere around 60 and specify that we want the cutoff of 60 and confirm. All right, so we've split our variable into two categories. So now it's dichotomous. And so we can just call this one, edit the label, and let's call this 1. And let's call this 0. All right, and the variable, the name of the variable they gave it was this. So let's do the exact same thing. So there's literally nothing that you can do on any of this other statistical software that you can do on the Chi-Squares platform. We just make it a bit more fun and a bit more visual and more intuitive, assuming that the person working on this is an 8-year-old child. That's our target audience. And so we tend to be a bit more colorful. But I mean, there's literally nothing you're trying to achieve that you won't be able to do that on the platform. All right, so this is our variable that we've created. Now let's go ahead and then fit the regression model as done in this particular use case. So they fit the model with the new variable, female, read, and science are the predictors. So let's do that. So let's come to estimates, regression analysis. We're going to select a binary logistic regression. Again, mind your language. Let's be precise in the language we use. The outcome is this one we just created, which is binary. The predictors, again, are female, read, science. Female, read, science. Let's select them in that order. Let's search for female, Okay, and then read, and then science. Okay, science is right here. Done selecting. All right, the platform automatically loads the reference groups. But if you noticed, again, the platform will automatically select the reference group with the highest sample size because that's best statistical practice. However, for now, we're going to put best statistical practice to the side and do whatever they did here exactly. Here, they said they use male as a reference group. So we're going to use male as a reference group just because we're trying to, for those who want to write the code later, they should be able to get the exact same result. So let's go back here and change the reference group from female to male. And then let's estimate. All right. So here we have our results here. This is the variable. These are the comparison groups. These are the odds ratios with 95% confidence intervals. And these are the p-values. All right, now let's compare with what they have. Let me actually, I'm tired of moving from page to page. So let me just create a copy of this and pull it out so we can compare better. All right, let's go back to this page. All right, so here we have our results on this side, and we have the results from this exercise here. So for, let's start with female versus male. We have an odds ratio of 4.40 with p-value of this, and they have this result, 1.48. Who can tell us what's happening? Why don't the results match? Any trials, any thoughts? Because we have female versus male, we have 4.40, right? They have 1.48. But it's the exact same binary logistic regression. So what's going on? Does anybody want to offer a guess or an explanation for what's happening? Any thoughts?
One answer, the reference group.
No, we're using the exact
General,
reference group.
the general on chi-squares was female. The
So
reference is not the same.
no, they use the same reference. They use male as a reference group. So here they're comparing females to males. The same way we're doing female versus male. Right? All right, here's a hint. What do they have here? What are they presenting here? And what are we presenting here? This is a very important point. So that you present the correct result. What is being presented here? And what are we presenting? So, okay, let's start with the easy one. On the chi-squares output, what is being presented?
Odds ratios.
Odds ratios, exactly. What they're presenting here are no odds ratios. These are log odds, the coefficients. So that means that to get this result, you will have to take one extra step of doing what? All right,
Calculate the odds ratio.
All right, let's look at this together.
Exponential of beta.
Exactly. You have to take the exponent of that, for example, right? So let's take the exponent. So this indicator here display the exponent of this 4.4, right? So you will now have to go and calculate the exponent of each of those results here to get this result here. But please do not report your results. I'm not exactly sure why they chose to report results in coefficients, because that's not generally how we interpret results. But the point I'm trying to establish is when you see discrepancies in any part of research, you want to be mindful. You want to pay close attention to see what is being reported here versus there. And it's also your job to make sure that you are reporting things in ways that are generally acceptable, generally common in the field. So in general, we report results from logistic regression as not as log odds or coefficients, but as odds ratios. And that's why on the Chisquares platform, we want to spare you the extra step of having to take exponents. Otherwise, that's what you have to do, right? You will always have to go ahead and take the exponents of each of those outputs to be able to get odds ratios, right? But if you now do that, you now get exactly what is here, right? So for the sake of just ease of interpretation, the platform does all of those extra steps for you so that you just have to focus on interpretation, right? Again, you have the results in form of a table that is both formatted and unformatted. You also have a plot as usual. And you also have the text, which explains what the results are. So, so here it says the following factors are associated with this. You have female versus male. The odds ratio is this. So you can see that the interpretation of the results presents it as adjusted odds ratios with the point estimates and corresponding 95% intervals. And that is presented consistently across the whole of the output. So again, the whole point is to remove that burden off you from having to say, geez, how am I supposed to interpret the results, right? Here, your job now is to say, how am I supposed to implement this result? What does this mean for my community? So that you don't get the interpretation wrong, right? The platform does that automatically for you. And then again, as usual, if you want to push the results to your manuscript, you can proceed that as usual. So that's how we fit models, and interpret results from a binary logistic regression. In general, it's always helpful to, when you're speaking with audiences that are lay audiences, you want to, let's switch to manuscripts, for example. Let me quickly show you. So again, in general, when you're speaking with lay audiences in general, try to avoid, avoid is a very strong word, but if you can, it's better for you to present results as 78%, lower, whatever, than to say 0.22. Most people find it very hard to wrap their head around things that are smaller than 1. Like when you say the odds were 0.22 times this group, people don't really understand it. Like, from experience, it's extremely hard for people to understand what you're saying. But if you tell them that the odds decreased by 78% in this group compared, people love percentages. So whenever you can express something as a percentage, they should absolutely try and do so, And that's why in this, the platform always provides that context for you as in that relative context, so that you can appropriately do so in your own word interpretation as well. All right, so we've covered 2 of the regressions. Let's look at the third one, which is ordinal. Again, ordinal logistic, as we said earlier, is used when you have a categorical variable that is ordered. It's very implied in the name. There's ordering. So let's look at use the case study here, and let's see what they did, and let's replicate it. So again, very, very important. You have to look at coefficients. Again, if you're using the Chisquares platform, you don't have to worry about all of those things. But if you are writing your own code yourself, you always have to worry about, am I presenting the results in the right format, right? Is this correct? So that you don't lead your audience astray. Imagine if you presented these results as odds ratios. That is completely wrong, and you said, oh, female had the odds ratios were 1.48. No, that's not what the results are saying. So you must be extremely, extremely careful when you're interpreting results this way, because you could lead your audience astray. And that's why on the Chisquares platform, all of those things are already resolved. So you don't have to worry about issues of interpretation, but just about what does this mean for my audience and how do I use it? All right, ordinal logistic regression. Again, remember, ordinal logistic regression is when we have a variable that is a categorical variable that is ordered. That's when we use ordered logistic regression. All right, so let's look at the data here. So description with data, let's see, where does it start from? So they're just giving examples here. For our data analysis below, we're going to expand on example 3. What's example 3? Okay, this one here. All right, a study looks at factors that influence, let me make this bigger, the decision of whether to apply to graduate school. College juniors are asked if they are unlikely, somewhat likely, or very likely to apply to graduate school. So now, right here off the bat, you can see that the variable here is ordered. This is like a Likert scale type question where they're like, oh, unlikely, somewhat likely, very likely. You can see that there's some hierarchy. There's some gradation. It's like a grade. Even though it's qualitative, it's still a grade, a qualitative scale. That is a perfect example for when we use ordinal logistic regression, when we have things that are measured on a kind of scale, where you can say that this is lowest and this is highest. It's obvious that it's a gradation. Hence, our outcome variable has 3 categories: data on parental educational status, whether the undergraduate institution is public or private, and current GPA is also collected. All right, so that's the context that we are setting or we're looking at. And so the data is here. We're going to interpret it. I'm going to read it in, and then we'll see how we can analyze and interpret the results. But again, for those of you who are going to be looking at it through your own code, well, this pages will be shared with you for you to be able to follow the code step by step. Of course, on the Chisquares platform, all of the technical issues have been resolved so that you only have to focus on interpretation of the results. All right, so let's go ahead and do just so. So let's replace this data set with Ordinal. Let's see. All right, so our data set, again, as usual, always visualize it, always inspect the data set before you jump into analysis. Don't just bring a data set and boom, you go to start analyzing it. Always see that what you are seeing is what you expect to see, right? So here I have, the outcome variable here have categories, 3 unique values. I expect to see 3 unique values. I can visualize to see what they look like. So I see unlikely, very likely, somewhat likely. All right, so that's great. Now let's go ahead and fit the model and see how we interpret the results. All right. So we'll go to estimate. Again, if you know what you're doing, always come here. If you don't know what you're doing, always come to Analysis Wizard. Again, Analysis Wizard is your home. If you're not sure what you're doing, you should just leave in there and not go anywhere. But you will still end up in the same place as anybody who came through in another direction, right? It's all about guidance and education and auto-correction. And so, but yeah, here we're just going to go directly to the regression of interest. So we're going to select ordinal logistic regression. Our outcome is apply. The platform automatically scans through the data set and sees that that is the only variable that is eligible. So if you come here and you don't even see a variable that selected, that means the platform has deemed that your variable is not eligible for ordinal. And the whole goal is to prevent this concept of garbage in, garbage out. Like, why do we have to allow garbage in the first place, right? So the platform, implements very strict validation criteria to ensure that whatever analysis comes out of it is accurate. So we're going to select apply as our outcome. The platform attempts to automatically sort the outcome for you, but you should always verify, because if it's qualitative, then it's like, okay, you want to make sure that it's correct. So let's select our predictors and then we'll come back to this. So the predictors here are believe they are, let's go back here. The parent education, public, and GPA. So let's go and select those two. So parent education, public, and GPA. Those are predictors. Again, the platform would automatically select your reference groups based on its best awareness of statistical practice. You can obviously change it. It has said the reference group is 0. In this case, it's looking at it prioritizes statistical precision when it's selecting reference groups. So it's not just some guesswork that's going on. It looks at the prospect of your model failing to converge based on sample size issues or other issues, and it prioritizes ensuring that your model comes out as well fit. Of course, you can choose to override the models, the platform's recommendations, but they're already made for you at default. So we've selected our predictors. Now, ordinal, the word ordinal means ordered. So it is extremely, extremely important for you to make sure that you make sure that the variable is ordered properly, right? The platform attempts to order the variables for you, but it may get it wrong, right? So please do not rely on the ordering that has been done by the platform. Now, when you're using, when you're fitting an ordered logistic regression, you have a very, very important choice to make. The choice is, do you want your results to come out in an ascending direction or a descending direction, right? And that's a matter of preference. It's your preference. Descending direction here means that you want to see if the outcome decreases as the predictor increases. That's what that descending means. Ascending means that you want to see if the outcome increases as the predictor increases. So you have to make that choice. Of course, the platform makes a default choice, but you can change it. You can say, all right, I don't want my results to come out that way. It's easier. I think for most people, this is more intuitive. Ascending is a more intuitive way of putting results from an ordered regression. So here you're saying that the odds of so-and-so increases as the predictor increases. So most people would wrap their head around that. But again, that's a choice that you have to make. Do I want my results to be in an increasing direction or in a decreasing direction? So you have to choose this. If you say you want to change it from descending to ascending, you just come here and say, all right, I want ascending. You should be aware that that will change how your results are interpreted, right? And so that's something you want to keep in mind. So if you select ascending, you want to make sure that you sort this appropriately. So here the instruction is, if you are selecting ascending, it says sort so that with the ascending option selected, the biggest, strongest, most intense, or most positive is at the bottom, and the smallest, weakest, least intense, or most negative is at the top. So here, very likely should be at the bottom, then somewhat likely, so we have to move this one down. So very likely, somewhat likely, unlikely. So we've sorted it. Always try and make sure that this is sorted well. Don't assume the platform sorted it for you, so you're fine. No, this is qualitative. This is plain text. It may not get it right. So it's your job to make sure that you sort it properly. Remember, we're talking about ordered regression. The key word here is order. It's your job to make sure that there is order in the sorting of the items based on the instructions. So we've sorted it properly now. The biggest is at the bottom, which is very likely, then somewhat likely, then unlikely. So we can click on done. The platform also tells you the direction here that you sorted. If we change the option from ascending to descending, the instruction will change. It will tell you to sort the other way around. And that has an impact on your results. So I'm emphasizing that because that is extremely, extremely important. But that's all you have to do, really. The next is just click on estimate. The platform takes those selections and then it will implement it in an ordered regression, and yep, it's finished. So here we have the results here. Let's compare those with what we have, and then let's look at the interpretation. All right, let's see. This is the ordered. So the coefficients, we don't want coefficients, we actually want these are the coefficients. Again, if you're writing your code yourself, you have to, it's so easy to make a mistake with these things, presenting the wrong results, failing to order, especially with models like Ordinal, failing to sort properly, not realizing the direction your results are being interpreted in. So there's ample room to make mistakes and to produce false or fake findings with more advanced models like this. So you have to be very careful, when you're fitting it. And this is particularly for those who are going to be writing their own code. All right, so here we have the results here. For parent education, we have 2.85. Let's just compare quickly. So parent education, 2.85, the confidence levels are there. For public, let's look at that. For public, we have 0.94, which is exactly what we got. And then for GPA, we have 1.85, which is exactly what we have. Again, regardless of the model, you are going to get exactly the same result, regardless of what software you use. I mean, hopefully the software is that, if it's a validated software, you should 100% of the time get the exact same results. Because like I said earlier, 1 + 1 is always 2 on any calculator. It doesn't matter whether the calculator was made in wherever it was made. These are basic math truths that do not change. So now let's focus on the interpretation, because that's what our session is all about, really. Now, but take note that the results are going to fundamentally change. Let's check the results. Now let's see what happens if we switch the results from ascending, which is what we have now, to descending. But take note of it, take note of it, the text, again, interpretation is all here for you. But for now, we just want to make sure that we can look at results when we switch direction and how that looks like. So I'm going to just let me take a screenshot of this so that we have let me look for a screenshot tool here. Sniping tool. Just a sec. All right, so I'm taking a screenshot of this so that we can preserve this in memory. So this is the screenshot here. We're going to compare the results when we switch. So again, this is reinforced to you that of course the outcome is going to change depending on whether you use ascending or descending, right? So now let's change the option here from ascending to descending. If you change the option, please make sure you come here and verify that it's still the same, right? So here, the instruction you've seen here has changed. You may not be aware of it, but the instruction is different now. So that with the descending option selected, the biggest, strongest, most intense is at the top, and the smallest, weakest, or least intense is at the bottom. Since we already sorted, the platform automatically flips the order for us so that we don't have to flip it ourselves. But that very first time, so you only have to worry about the sorting once. If you've sorted it carefully, then everything is fine. You don't have to worry about other things. So we're done. We can then apply the estimation now based on so here you see now, are these results wrong? Obviously not. They're not wrong. It's the interpretation that has to change, right? So what the point we're trying to make, let me pull up the previous one. This is a bit tiny. Let me expand it. So of course, everything is going to change. Now, this doesn't mean that this is wrong. That's not what we mean at all. They are both right, right? This is right, this is right. It is your job to know the content. And of course, if you're using the Chisquares platform, the interpretation will be consistent, right? You don't have to worry about the interpretation of the results. The care is if you're running the code on your own, you got to know the direction, because how you feed in the vector determines everything, and so you don't want to come up with the wrong results that are misleading the public when you're saying that this is causing death when it's actually saving when it's actually saving lives, so that is extremely, extremely important. I cannot emphasize it enough. So you want to be very careful that with ordinal logistic regression, you pick the right direction and you understand the interpretation. Again, if you're using the Chi-squares platform, you don't have to worry about those nuances, because those are automatically incorporated by the platform and accounted for. But, again, if you're using, going to run the code on your own, you got to be very, very, very careful, because you could easily make a mistake, a very gross mistake, just like that. All right, now let's move on to the next model. Multinomial, we have this, and let's see how that plays out. So again, multinomial is, remember, we use it when we have a categorical variable that is not ordered. So categorical variable that is ordered, we use ordered regression. Categorical variable that is not ordered, we use multinomial. So let's see how that works out. So here, the example is saying, let's look at what we have here. Okay, the data set contains variables on 200 students. The outcome variable is program type prog. The predictor variables are socioeconomic status, which is SES, and writing score, which is write. So, all right, they have a lot of things here, a lot of analysis. So here we can see that this is the output they have here. All right, let's fix it first, and then let's make sense of it. All right. So remember that we use a multinomial when we have a categorical variable that is not ordered. If I'm looking at the types of transportation that people use, and people say, I use a car, or I use a train, or I use a bike, there's no order in those things, right? So in the example we have here, we have 3 program types. There's general, there's academic, there's vocation. There's no order there. So we're trying to see, how does the choice of one, or let's fit it first. Maybe when we fit it, that will make more sense. So let's come here, let's go back and choose the data sets that correspond to what we are using, which is the nominal. So I'm going to replace this data set with multinomial. Whenever you upload a new data set, the platform always asks you whether you want to weight the data. So that if you want to weight the data, you just say yes, and you supply the variables for weight and all of that, and that's it. But if you're not weighting the data, you can just say no. But that will always pop up whenever you upload a new data set, so that you can't say, oh, I was supposed to weight there and I forgot. There's no forgetting here. We'll always remind you whether or not you might need to weight the data, so that it's always at the top of your mind. All right, so let's see. We have our data set again. Always inspect your data when you bring it up. So here we have the key variables. Let's visualize them. So those are program types, academic, general, and vocation, and that looks fine. And then, all right, let's fit our model. So come to estimate regression analysis. We're going to select multinomial. All right, so the outcome here is program type. Outcome variable, program type. Sorry, I zoomed out so you guys can see clearly. So program type. Now, the special thing about multinomial regression is that it requires you to select a reference category for the outcome. If you recall, this is the first time for any regression we're doing that we've had to select a reference category for the outcome. We've been consistently selecting reference categories for the predictors, but not for the outcome. Well, that's how multinomial regressions are designed. You will have to select, okay, what is the reference group for this outcome of interest, right? The platform, again, automatically selects a reference group for you based on its best judgment of what makes sense statistically, right? So here, for example, it looks at all of these groups and say, well, the one with the largest sample size is academic. Academic should definitely be the reference group. And that could be a very logical thing to do. However, for the sake of this demo, we're going to put statistical reasoning aside and just copy whatever these guys did here. Right? Here they used which one did they use? They used academic. Oh, okay. Sorry, they actually used academic too. My bad. So they also use academic as a reference group, which makes perfect statistical sense because it has a larger sample size and that ensures adequate power. Taking a group with a small sample size is like allowing a weak general to lead you into battle. You're going to get slaughtered. So you want for robust findings, you want to consider the sample size for the reference category as well. Now let's select the predictors. The predictors here are, let's see, what are they? SES and right. So SES and right. So the SES here, again, you have to consider things, right? Do you want to use, statistically, it makes sense to use the one with the largest sample size. However, sometimes we have to pay attention to issues about common sense. Sometimes common sense has to play a role, especially when you have things that are small, smaller, smallest, big, bigger, biggest. It kind of feels very awkward picking the one in the middle to be the reference group. In those kind of contexts, it's usually more intuitive to say the ones at the extreme should be the reference group. So either the smallest or the biggest, because it's like, okay, smack in the middle, you just chose the one that is middle. Again, statistically, this makes sense, but life is not all about statistics. We also have to consider about other things like intuition, right? And clarity of explanation. And so I'm sure this is that for that reason why these guys used number 1 as the lowest, as a reference group. And how do I know that it's number 1? Well, because you have results for number 2 and number 3. The one that is not present is the reference group. So they are likely using the lowest group as the reference group. So for that reason, we're going to change our reference group to low. And the Chisquares platform always presents to you the sample sizes for each of those groups so that you have some basis for choosing. It's not that you're just choosing blindly and say, I wonder which one I should use as reference group. So we automatically choose one for you, but we also provide you with context so that you can select whichever other one you want. So in this case, we're going to just go ahead with low to align with what was selected there. All right, so here we have our results. So logistic regression, the multinomial regression is a bit different from the others because here we're going to present results for the outcome here, general versus academic. So each category of the outcome will be compared to the reference group for the outcome. And perhaps let's just look at an image first. Let's look at it. Since they say a picture speaks 1,000 words, let's look at this. So here you have, remember we had 3 categories for the outcome. We had general, academic, and vocation, right? And we used the academic as a reference group. So that means that we're presenting results for the general and the vocation, each compared to academic. So we're saying that's why you have 2 sets of results here. The ones in blue, which corresponds to general versus academic, and the ones in red, which corresponds to vocation versus academic. So first and first, as usual, let's compare the results with the outputs we have here. So let me pull out this and put them side by side. All right, so these are coefficients. Again, you want to be very, very, very careful when you interpreting coefficients, right? You don't want to make the mistake of taking coefficients and interpreting them as odds ratios because that's a disaster. Again, if you're using the Chisquares platform, all of that is automatically handled already. But if you, again, for those who write their own code, well, you just want to be very, very extremely careful of that. All right, now let's look at the results that have been exponentiated. So here we have, this is general versus academic. So this is what it means here. The general here, it actually means it's not just general, it's general versus academic. So that's what you're actually seeing here, general versus academic. For the SES group here, the middle SES group, oops. Oh, sorry. So for the, let me just move this to one side and then we can display it again. All right. So for the middle group, general versus academic, we have the odds ratio of 0.59, which is what we have here, right? 0.59. And then for the highest group, which is 3, we have 0.31, which is what we have here. And then the rest of the results are also consistent, right? When we look at 1.3, 1.338, which is, to 2 decimal places, 1.34. And then for right, you have 0.89, 0.89. So the results are exactly what you would expect. But it's not just about generating results, it's also about knowing how to interpret them, right? So the point we're trying to make here is that in a multinomial logistic regression, you're going to have results presented for each category and compared to the reference group for that outcome. So here we had 3 categories of the outcome. So we're going to have 2 sets of results. One, general versus academic, the other one's vocational versus academic. If we had 4 categories, we're going to have 3 sets of results. If we had 5, we're going to have 4 sets, each being compared with the reference group. So the complication, with this is that it becomes quite a mouthful in terms of trying to interpret it. But again, all of that text is explained for you in terms of the interpretation of the results in here. All right, so I'm going to stop here. I think we've been speaking for quite a while. I'm sure people have questions, so we can take questions that people might have, so that we can have ample time to accommodate them. So, any questions?
Yes, so I'll start by reading. If you want to ask a question verbally, you're welcome to raise your hand and we will let you ask. I'll start by reading. Does selection bias only apply to experimental studies, or can it occur in a one-time questionnaire study as well?
Yeah, it can also occur in a one-time question, in a survey, right? Here we'll talk about 2 types of biases that are aspects of selection bias. We'll talk about non-response bias and non-coverage bias. Non-coverage bias says that, it's like the cover of a pot, right? If imagine you had a very big pot and the cover doesn't cover it fully. That gives a very powerful mental image of what non-coverage bias is. So it means that your sampling frame does not cover the pot. The pot here is the population. So you have a list of people to sample from, but that list doesn't cover everybody. So a practical example, let's say you're doing a survey of the US households, right? Household survey, or anywhere you're going, let's say, in the US, for example, household survey. Well, household survey means you're going to households. It means that you are not going to prisons. You're not going to places that administer care to the elderly. You're not going to military barracks. So that means that all those other guys are not covered in your sampling frame. So if you are claiming that your survey is a survey of all Americans, then it's obvious that there's non-coverage bias, which is studied because it doesn't really cover everybody. So the only way to get out of that sticky situation is to say that, well, those people actually are not part of my study. My study is just a survey of the non-institutionalized US households. Now you're fine because you never made claims that you have carefully and systematically removed those people so that, now you have no issue of non-coverage bias. So, but the second part of that dynamic is non-response bias, which means that I went to the homes of people who were inside that sampling frame and some did not answer, right? So those are two sources of selection bias, even in surveys, that we have to worry about. Non-coverage bias means my sampling frame includes A, B, and C, but does not include D, E, and F. Non-response bias means that even though I included A, B, and C, I went to A and he did not answer, right? There's the systematic difference between the responses of A versus that of B and C, even though they were included in the sampling frame. So bottom line, yeah, you can have selection bias not just in experimental studies, but also in surveys.
Thanks, Prof. Daniel.
Thank you, Prof. Once more. Prof, please, I want to be clarified on this multinomial. Is it the same thing as when you talk of, is it applicable when you talk of when there is composite outcome? You know, when the outcome is, there are many outcomes you're looking at, and you're looking at predictor variables that can affect them. Is it multinomial that is rightly applicable there?
So the composite variable, a composite outcome.
Am I?
Yeah, we had it clearly, yes.
Okay.
Yeah. A composite variable simply means that it's a variable made up of two or more variables, right? And so, but at the end of the day, it's still one variable. I may create a variable, for example, current cigarette smoking, that is determined by two different variables. Have you ever smoked cigarettes, and do you smoke cigarettes now? Right? That's a composite variable. And so on the basis of that, I can categorize individuals as current smokers, former smokers, and never smokers. So I have a composite variable. It has multiple categories. Those categories are not ordered. And so, yes, I can still use multinomial regression. However, I suspect that what you are referring to might be a scenario where you have multiple outcomes, not just that you have a composite variable. But that you have multiple outcomes that you are trying to explore. And in that case, that is not a use case for multinomial logistic regression. All right. Next question, please.
Super.
Looking at down the questions.
Oh, sorry, muted. Neliswa? Neliswa, you can unmute. Okay. We can't hear you. All right, I'll just read one in the meantime. What is the difference between multivariable and multivariate analysis?
Multivariable means we have all the things we've done here are multivariable, because in each case we had one single outcome and one or more predictors, right? One single outcome. But in some instances, we might have not one outcome. So for example, what the last person who asked the question was, the question hinted at a scenario where we might have multiple outcomes, right? It's not just that you have one outcome, like whichever outcome we're exploring, but there are many outcomes. In that case, it's multivariate, because there's not just one outcome and predictors. There are multiple outcomes. So if we have, for example, a structural equation modeling, right? In that case, we might have multiple outcomes we're interested in, and seeing how this one outcome affects the other one, and then how they are related with the predictors. We're going to have a multivariate ANOVA. We can have things like factor analysis or principal component analysis, where we don't have predictors per se, but everything is an outcome. It's not as if we're trying to see how does the predictor influence this outcome, but we have a whole bunch of outcomes, and we're trying to reduce the dimensionality of the data, right? In those cases, it's not just one outcome and a bunch of predictors. So whenever you have a scenario where you have more than one outcome, that is when you use the word multivariate. But when you have only one outcome, it's multivariable. So one outcome and multiple predictors is multivariable. But in reality, most times, in almost 99% of the times, when people actually say multivariate, you find that they actually mean multivariable. But that's the difference.
Thank you, Prof. Poisson regression, you talked about equidispersion of standard deviation roughly equal to mean. What of if we have standard error, what will it be equal to? Still maintain equidispersion for a population data?
I'm trying to understand what you mean. So are you saying that you don't have standard error? You don't have the standard deviation, but you have a standard error. Well, there's a mathematical relationship between the standard error and the standard deviation, right? Which is a function of the square root of the sample size. So you can calculate that, you can convert that and use that accordingly.
Okay. Any other questions? I had a cross-sectional study for 3 categories of students, third year, 15 students, fourth year, 50, and fifth, about 10 students. Can I do anything with this data? I failed to collect the appropriate sample size.
Well, if the sample size is not enough relative to what you had calculated, you can still explore it qualitatively. That means that you can still look at and say, oh, wow, I see a general pattern, but not that, oh, there's a p-value of this and p-value here. You analyze it more qualitatively, which means in the absence of p-values, but you're just trying to see whether there are patterns. And that could then form the framework for your future studies.
Thank you. And by the way, the attendance register has been posted. Kindly complete it and also evaluate the session. Thank you. Next question, how do you incorporate the use of sample weights in the platform?
The platform allows you to sampling weights. I'm going to assume that you mean in the analysis. So in that case, you will simply select the weight variables. And that's all you need to do. The platform will automatically just account for them. You don't have to account for them. So it's not like in other software like Stata or R, where there is a separate command for, let's say you want to do a chi-square test. There's a separate command for unweighted and another one for weighted. No, that's not how we've engineered chi-squares at all. You don't have to worry about all of those nuances. All you have to do is set the weights, the PSU, and once the data changes to weighted mode, everything takes place automatically in the background. So you don't have to account for anything apart from just those selections.
Thank you. Do we have any more questions? Earlier on, they asked Prof why you used data.
Why I use what? Stata?
Yes, for the exponential calculations.
Because I used it as, well, because the
Not the
original
chi-squares
analysis.
platform.
Because the original
Yes.
analysis was performed in Stata. So to make sure that you could see like to like. And in fact, but just to be clear, the fact that we have use cases doesn't mean I don't use other tools. And this definitely not to tell you that you shouldn't use other tools. You can use whatever tool you want. So I want to be very clear on that, right? This is not a conversion session. You can use whatever tool you want to do for your work. I use the Kaiser's platform for a lot of my work, but I also use other tools for other things. So that's a very funny question.
Okay. Any other questions? What is the token to continue survey? Okay. You need to click on start survey, not continue survey. Ishmael, start survey. You clicked on continue post survey. Okay. It seems that's all.
All right, awesome.
No more questions.
Thanks, everyone. I guess we'll see you tomorrow then.
Do you have anything to say about the homework, Prof? Yesterday's homework? We didn't get any.
Well, okay. Well, they should try and do homework. Please try and do homework. I will share some additional homework, and then I'm going to post the answers for those from yesterday as a short video recording, so you can go over it. Do you have anything to say about the homework, Lungile?
No, just that they should give it a try. No one shared their homework, what they did. So they should give it a try. That's all I can say.
Yeah, but I find that whenever we don't give homework, they're like, oh, give us homework. When we give homework, they're like, oh, you don't do it. I'm very confused. Do you want homework or not?
They want it. They just want it.
They want the idea of homework. Okay.
Just to complete the experience, but nothing from their end.
Yeah. I see that. I see you all in high definition, clearly. All right, I'm going to post another homework too, though.
Please do. At least give the people what they want.
All right, sounds good.
All right, thank you.
All right, thanks so much, guys. I'll see you tomorrow.
Oscar, you have your hand up. Sorry, Prof.
Okay.
One more hand before you go.
Okay, sure.
All right, thank you. Thank you very much. Prof, I want to find out whether your platform has a provision for, because my study has to do with a randomized control trial, and I'm analyzing my database on the various two districts. But when I have the data like let's say, for instance, sex, I want to break the data down into district A having this, how do we call it, sex, and district B have also sex, so that I can be able to compare how it varies. I want to find out whether your platform have that provision. Instead, I use bisets and those things to divide it, but I find it so difficult when I'm not used to the code. So I want to find out whether you have a simplest way of doing it. Thank you very much.
Yeah, you can use the you know, you see my screen. You can use the cross-tabulate function. So for example, I want to tabulate this and this, let's say, and I want to I want to stratify by, let's say, another variable. Let's say let me look for another variable that is by school type, right? So so this is the equivalent of saying by. So this is saying by this group and by this group. Does that make sense?
Oh, okay.
Yeah, all right.
Okay, thank you very much, Prof.
You're welcome, yes. How do I stop screen? All right, thanks so much. See you guys tomorrow then. Cheers.
Bye.
Bye. Yeah.
Thanks, everyone. Have a good evening. Sorry, Nelisa, that she couldn't ask your question, but hopefully tomorrow your mic will allow you.
According to the New England Journal of Medicine, it takes an average of 4 years to develop a research manuscript, from start to finish. 4 years.
And you're telling me all you got in 4 years was one paper? You could earn another degree. Elon Musk launched a rocket and brought it back. They made all 4 seasons of Stranger Things. A toddler could grow into a talking, tantrum-throwing preschooler. You could get dumped, recover, and find true love.
Writing a paper isn't rocket science, but people say it's supposed to be hard. Spoiler alert, everything feels hard when you're using the wrong tools. There's a better way. Explore a smarter, faster, more human approach with Chisquares. With Chisquares, you can write your entire manuscript. Analysis, results, writing, and citation in just 1 day. Chi-Squares. One platform, 1 day, one finished paper. Try it.